Okay, so I believe this is the correct request. I'm not 100% sure. But anyway, I'm going to try to solve this one where we've got some block. It is going to be compressed some, dadgummit. Okay, it is going to be compressed down this particular, spring in that direction, some distance. It looks like it's going to be 20 centimeters, 0.20 centimeters. And then it's going to be released. And then we're going to talk about what happens. Now, in order to make this a little bit easier on myself, I have 3 copies, so I don't have to, so I can kind of do each of these questions individually. Okay, so the velocity of block immediately after it leaves the spring. So basically, you're going to pull this thing back to some position over here. Let's imagine there's like some sort of like block that this thing is sitting on, right? Okay, so it's going to go back 20 centimeters. Let's go ahead and zoom in here. Let's get rid of all this. Okay, so we're going to pull it back. Can I get a different color? Thank you. Okay, so it's going to go back this way by 0.20 meters. And then it's going to get released. Okay, so if we call its original unsqueezed position A, and then it's going to go to position B. Okay, so now what we're asking is we want to know what's happening to it once it gets back to A, right? When it has been released and before it starts to kind of, experience whatever is going to happen to it along the incline. Now, I do want to note that we kind of said that it was going to be, this whole thing was going to be frictional. Okay, but when I gave you this test, I said, let's ignore the friction in this particular section, okay? So in that section, we will say it is frictionless, okay? And the reason for that, it's really just about not making the problem too complicated. Anyway, so let's go ahead and do this. Okay, so we're gonna start by, what do we want to know? Oh, we want to know the velocity at, I guess we'll call that C, all right? So we'll call this, so you're going to pull it back from A back to B, and then you're going to release it, and it's going to go back to A. And maybe when it gets back to A, we'll call that A prime. So that'll be A at a future, at a later time, right? So it's at A twice. So we want to know, what we're going to do is we're going to solve this problem from B until it goes to A prime, okay? So so let's start, and let's imagine this mass that's moving up and down this thing. All right, so the formula for this, okay, work non-conserved equals a change in KE plus the change in potential energy. Okay, so work non-conserved, blah blah blah. So because we say that there's no friction here, cool. That means when I draw my free body diagram, let's see, that means what forces are on the mass? Well, we've got a gravity going down. We don't have a friction from B to A prime, right? So this is from B to A prime. Okay, so this is going to be my final. This is going to be my initial. Okay, and so from B to A prime, let's see, we've got gravity. Friction would be here, but we don't have that, right? So we're not worried about that. We've got a normal force going this way, and we've got a force of the spring going this way, okay? So these are the terms that we need to think about, all right? And as we think about them, we're not worried about the normal force because it's perpendicular to the movement, okay? So that doesn't give us any work. And then the force of the spring, this is a conserved force, so this is going to be a potential energy due to the spring. And the force of gravity, this is going to be potential energy due to the spring. Okay, cool. And so now we just need to evaluate these two things and kinetic energy from B to A prime. Okay, cool. So we're going to go up here. So because I've got two potential energies and no non-conserved work, this is going to be a 0. Okay, so the change in kinetic energy. Okay, so at A prime, we're going to have kinetic energy, 1/2 mVA prime squared. Okay, whereas at B, the velocity of B equals 0, right? Because you pulled it back and you're holding it there before you release it. So minus 0. That's the change in kinetic energy. All right, the change in the potential energy plus, let's see, so let's just do gravity first. Gravity is usually the easier one, so that'll be mg times delta y, okay? And we'll evaluate that delta y in a second. Maybe if I did it this way, let's, how do we want to do that? Okay, here's the delta y, right? This is the distance up we went, right here. And we know that this is 20 centimeters right here, right? So maybe I don't know what I want to call that 20 centimeters. Give me a variable name for that. I'll call that x, right? Because x is the amount the spring has been compressed. So if we scroll in on this little thing, if this is x, and this is x sine theta, I can't really see that because of the way that where I wrote it. But this distance right here, that's x sine theta. Okay, that's the vertical, right? And it's going up. So final a prime minus the initial is going to give me a positive number. So x sine theta. Okay, mg, and then this will be x sine theta, right? A positive x sine theta. Okay, so that's the potential energy due to the gravity. And now we got to do the potential energy due to the spring. Okay, so the potential energy due to the spring is, well, we know it's going to be plus 1/2 k. Now the final is going to be here, where it's completely, where the spring is now relaxed. Okay, so x equals 0 there. So 0 squared minus 1/2 k. And the initial is when x is 0.20 meters, right? So we'll just put in the x right there, x squared. Okay, so that is our ginormous equation to figure out this first bit. I want to check my key and make sure that I'm following along pretty well correctly. Yeah, so I guess we could call this xb if we wanted to, right? Okay, so let's go ahead and let's solve this sucker. Or really, I guess then this is xb as well. Okay, so what are we solving for? Oh, we're solving for the velocity. So this is what we're looking for. So that's what we're going to try to isolate. This term goes away because that adds up to 0. This term goes away because that goes to 0. So it looks like I've got negative 1/2 mva prime squared equals mgxb sine theta minus 1/2 kxb squared. Okay, so va prime squared equal, let's get rid of that squared. We know we're going to get a giant square root on top of all of this. Multiply everything by 2 and divide everything by m. So 2gxb sine theta minus mkxb squared. I think that's wrong. I think this m, right, we're dividing by m. So this is going to be x over m. Yeah, that's right. Okay. So now we'll plug and chug. I'll just pause and plug and chug. Okay, I'm getting 7.8035 meters per second. I will note that I made a sign error earlier, so you'll see that in red. That's just algebraic, right? So here, 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 and here. Basically, it was this minus sign. I forgot to divide by it. Okay, so with sig figs, I believe there's 2 sig figs in this problem, so we'd say VA prime equals 7.8 meters per second. Okay, cool. All right, so that's the velocity of the block when it leaves the spring. All right, cool. B, let's go over here. B, the velocity of the block after it has traveled up the slope for 1.2 meters. Okay, so now we've got this particular situation here. And the spring is pulled back. It is at a position like, the mass has been moved to a position here. All right, so it has compressed that spring a grand total of 0.20 meters. I guess maybe, yeah, I don't know. It depends on how we want to do this. My dog, can you hear my dog barking in the background? Okay, so 0.20 meters. And then, and that's all frictionless, blah, 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 blah. And it's going to go up 1.20 meters. And we want to know how fast it's going at that point. Okay, now the problem is this 1.20 meters, this is all friction full. Okay, so there's friction from here all the way to the end. So we do have to deal with friction. Okay, so if we consider, the free body diagram of our block, we've got the force of the spring is going this way. We've got gravity going down. Got a normal force going this way. And we've got friction going this way. Okay, so we've got all of these four forces to consider. And if I want to think about all of them in order, normal, force of the spring, force of friction, force of gravity. Okay, so I want to consider what kind of work they do. Okay, so the normal force is a non-conserved. What else is non-conserved? Friction is non-conserved. However, the normal force is perpendicular to the movement in this case. So work due to normal is 0. And force of friction is non-conserved. It is parallel, however, it is anti-parallel, right? It's always against the motion. So the work due to friction is less than 0. Okay. Now, the force of gravity and the force of the spring, these are conserved. So they're going to be potential energy, right? So this is potential energy. Well, I guess we could say potential energy, right? So the next thing we need to think about is, are these things, potential energy, do they exist at our starting point, which I don't remember what I called these in the last one. What did we call that? We called it B, where it was all the way wound up. Yes, B, where it's all the way wound up. So we'll say at B, where it's all the way squeezed, and then at C, when it is 1.2 meters up the slope. Okay, and I think, the potential energy due to the spring, okay, potential energy at B is real, it exists, okay, whereas potential energy due to the spring at C is 0. Okay, and then for the gravitational potential energy at B, well, we might call that 0, right? Because we need somewhere to be 0. So maybe we make this point right here, y equals 0. And then the potential energy at C is going to be, looks like it's going to be all of this. Sine of, so it's going to be this distance right here, right? So that's going to be, 1.4 sine. So this is going to be x, and this is d. So this will be x plus d sine of that angle. Right, so that's the distance. So it'll be mg x plus d sine theta. Woo. Okay, I will note that if you look at the key that I posted on Canvas, I did not do x plus d. I just did d. But that is also because when I did this problem, I did not start the problem here. I started the problem here using the values that I'd already gotten from the previous set. So I think, if I do this correctly, I'll end up with the same answer, okay? This is just like a slightly different way to do it, okay? Because for that problem, I went from A prime, A prime is right here, A prime to C. So anyway, so just something to note. Okay, so setting up my equation, here we go. Give me that nice black color. Work non-conserved equals the change in KE plus the change in the PE. Okay, work non-conserved, in this case, note, so this one, nope, okay, because it's perpendicular. So we got the force of friction, and it's going to be negative. So negative force of friction times whatever distance it's going to travel through the friction, right? So the friction does not happen during the first 0.2 meters. So it will, however, happen during this 1.20 meters, so it's going to be D, okay, where D is 1.2. Okay, equals the change in kinetic energy. Well, at B, always remember this is going from B to C, okay? So at B, my initial condition, kinetic energy is 0, minus 0. But at C, it's cruising, right? Presumably, so 1/2 mvc squared. Okay, so there's my final minus my initial for kinetic energy. All right, so for potential energy, right? Which types do I have? Well, I've got the spring potential energy, and I've got the gravitational potential energy. So I usually start with gravitational potential energy, so it's going to be mg times the delta y, which I had already kind of figured out what that was. So it'll be x plus d times the sine of theta. Cool. And then what's the next thing? Oh, now we need the potential energy due to the spring, right? So we note that in its initial position, it's got a potential energy due to the spring, and in its final position, it does not. So plus 0 is its final potential energy due to the spring, minus initial potential, which is 1/2, minus 1/2 k times x, because that's how much it's been squeezed. Okay, and that is a pretty ugly equation, right? But we can deal with it. The problem with this equation is looking good, but we don't have that, right? We've got the distance, we've got the mass, this is what we're looking for. We've got the mass, we've got the g, we've got both these distances, we got the angle, we got k, we got x. Okay, so we need the force of friction. Okay, so the force of friction in this case, I guess I can scroll in on this free body diagram right here. I've already done the work for that, right? So here's our negative y direction. Here's our positive y direction. Okay, if I sum forces in the y direction, we know that this is going to be theta. So that means that this one right here, and this one right here, so this is Fg cosine theta because it is adjacent to that angle. And this is Fg sine theta, Fg sine theta. So this then is mg cosine theta, right? If I just do another line of it. So that then equals to the normal force because they're going to be equal and opposite to keep this thing from accelerating in that direction. mg cosine theta. And then the force of friction then is mu mg cosine theta. I got to work on these g's. They're starting to look like s's. Anyway, so we're going to go ahead and plug that in. Okay, so where are we? We're over here. Oh, it doesn't look like the m's are going to be able to cancel, which is stupid annoying. Okay, so we're left with this huge expression, mu mg cosine theta d equals 1/2 mvc squared plus mgx plus d sine theta minus 1/2 kx squared. Okay, and all of that, this is the one that we're going to solve for. Okay, let's see. 1/2 mvc squared equals, so it's going to stay where it is, which means this is negative, that's positive, so we'll have 1/2 kx squared. You know what, I'm going to maybe I'll let you watch me do this algebra just in case I'm if that's helpful for you. Mu mg cosine theta d. I need this term, which is negative, minus mg x plus d sine theta. Okay, so I'm going to multiply everything by 2 over m. So VC equals, multiply this by 2 over m, kx squared over m, minus 2 mu g cosine theta d, minus 2 gx plus d sine theta. Okay, and we'll put giant square root on all of that. Okay, big, nasty, ugly. We love it anyway. All right, so again, this is a little bit different than my key, but, you know, McKee chose to start from a position that had no spring energy, but had kinetic energy instead, okay? So let's see what happens if we plug and chug. Okay, I think that this is about how it looks. It does look something like this. Okay. Oh, it should be a squared here. If I'm staring at my units here. This one looks good units-wise. This one looks good units-wise. Okay, good. So if I plug all this into the calculator, okay, let's see. Again, I'm still using this stupid phone. So I get the square root of 40.967, and the units on all of those things is meters squared over seconds squared. So if I do the velocity at c, if I do the square root there, let's raise this to the 0.5 power, and I get 6.4006, and hopefully that matches the key. 6.4005, okay. Oh, yeah, I think I probably had a rounding error on the key. Anyway, so how many sig figs are we doing on this problem? Two. And this is probably where I should have ended this problem. This last bit was a little bit too much. Like this was plenty good enough for separating, you know, the old separating men from the boys sort of things. This thing was plenty good. I'm going to do the C part, but I think it was perhaps a touch too hard. Okay, so let me go over here. Hold on, my dog is barking like a crazy dog. What the? Where's? Oh, okay. I drew all over this one. Interesting. Okay, let me do this. You can go over here, and let's solve the C part. Okay, and let's go ahead and erase this. Okay. All right, so maybe this C part separates, if the B part separates the men from the boys, this separates the men from the champions. I don't know. All right, so the velocity of the block when it hits the spring the second time. So that's what we're looking for, okay? And I think I called this position B when it went all the way backwards here. So let's, let me see here. So it gets pulled back some distance. All right, let's kind of do it a color that maybe we'll see through. Okay, so it got pulled back some distance. That distance it got pulled back is called X. Okay, and you know, X is, this is 0.20 meters. Okay, so we have to consider what D is at this point. D is the distance that let's say the front of the block, we'll just call that, right? The block is going forward and forward and forward. D is the distance to which the block slides before it stops. At which point, the block is going to slide back down D and hit that spring again, right? And we note that, of course, because we remember this from the last part, that all along this portion right here, it's frictional. Okay, so in other words, the work done due to friction, the work non-conserved, is going to be negative force of friction times that distance, but it's going to do it twice, right? Because it's going to go up and it's going to come back. So it's going to be negative force of friction times 2 times that distance, right? Because it's got forward and then back. Okay, so that's like a really key point to this whole thing. Okay, so if I wanted to solve this sucker, and, you know, and I wanted to go from, you know, pulled all the way back, which I think we call that position B. And basically I'm going to go from, well, where do I want to put the letter B? I think we'll put B right here. All right? And so now we're going to pass through A prime. And then we're going to go all the way up here to, I don't know what we call the stopping point. What do we call the 1.2? Did I have a name for 1.2 over here? Well, I called it C. So we're going to pass C, and we're going to keep going. So C is somewhere along here. And we're going to keep going to D. And then we're going to slide all the way back here. And I'm going to get to A again, but this will be A double prime, right? So I want to go from B to A double prime. Okay, B to A double prime. Okay, and I want to think about all the forces that are you know, acting on this thing. So here's my like composite free body diagram. So the whole time there's a normal force. During some of the time there's a spring force. There's a force due to gravity. And the force of friction, which will go in either direction, right? Sometimes it's going to go this way, sometimes it's going to go that way, depending on whether or not the object is going uphill or downhill, right? Okay, so that's kind of a lot, right? So if I want to go from B to A prime, then I need to consider those four forces, right? So let's see here, force normal, force due to gravity, force of friction, and force of the spring, okay? And I want to think about the work that each of these is doing. Okay, the normal force is non-conserved, gravitational force is conserved, the friction is non-conserved, and the spring is conserved. Okay, cool. So the normal force, however, is perpendicular to the motion, so the work due to the normal is 0. So we are going to ignore that entire column, right? Or row. Get out of here, punk. All right, now the force of gravity, it is conserved, so we will do potential energy. Okay, great. Okay, now the force of friction is non-conserved, and it is parallel, however, it's like anti-parallel, right? So we're going to get the work due to friction is going to be negative. Work due to friction is less than 0. Okay. Now the force of the spring, on the other hand, that is potential energy, so good to go. All right, so let's go ahead and consider. Okay, so these are the three things we need to do. We've got two sources of potential energy, spring and gravity, and we've got one non-conserved work. Okay, so here we go. So let's see here. Work, non-conserved, plus the change in KE, plus the change in PE. Okay, so work due to friction, there's our non-conserved work, is going to be negative force of friction times 2D, right? Okay, equals the change in kinetic energy from, let's see here, B, when it's from B to A double prime. At B, which is, oh, sorry, let's start at A double prime, because that's the final, right? We always want to do final volumes initial. I don't know what that is. So 1/2 mVA double prime squared, that's my final kinetic energy, minus my initial kinetic energy. Well, my initial is at B, so right here, where I have, it's not moving yet, right? It's being held in place. Okay. Now, let's go to the potential energy, right? I've got both forms of potential energy here. I've got this one and I've got this one. Okay, so let's start with gravity first. mg times the change in height. Okay, so I'm going from B to A double prime. So here's B, here's A double prime. Okay, so that distance in height, if I could draw the triangle here, let's see, here's just like that. Well, that's a really horrible triangle. Maybe I should zoom in here. Okay, so here we go. So it's, you can do it. So it's like this and like that, right? So here's my angle theta. This is a distance x. So this distance in height is going to be x sine theta. Okay, kind of hard to see, but x sine theta. Okay, so let's go back over here. So it's going to be mg x sine theta. Okay, because that's the change in the height. Okay, and it is a positive change in height. Okay, so then let's see, what else do we have here? Oh, we need the potential energy due to the spring. Okay, plus, so the final potential energy of the spring at A double prime, when this thing is just tapping that spring again, the spring is not compressed. And then let's subtract the initial spring energy, which is at B, which is where it is negative 1/2 kx squared. Okay, so there you go. There's our equation. I don't remember if this is how I did it on the key. Let's see, did I do it this way on the key? No, it does not appear that I did. Okay, so anyway, so this is a fairly complicated equation. It's a little bit annoying. And the problem with this equation, it has one big problem. Let's see. Well, I guess it's got one small problem. I don't have force of friction, but the other big problem is I don't know what that D is, right? The temptation is to say it's 1.2, but we really don't know how high up it slides before it stops, right? I know the mass. This is what I'm looking for. I know mass, I know gravity, I know X, I know the angle, I know K, I know X. So none of that's a problem. The force of friction is not that big of a problem, right? Because I can easily make that negative mu m g cosine theta, just like I did last time. I can put the 2 out here. And then, but this is the problem, is this D right here. Because I don't know what that is. Equals 1/2 mva double prime squared plus mgx sine theta minus 1/2 kx squared. Okay, again, this was a doozy of a problem. I don't think anybody got it all the way, although 2 of you at least were on the right track. Okay, so the big problem here is we don't know what this D is, but we can figure out what that D is. Okay, so what we're going to do is we're going to go up here and we'll figure out D. Okay? So that distance is this distance right here. And again, I'm just going to go from B to this spot D. Okay, so B to D. B to D. Okay, so from B to D, let's see here, work not conserved equals the change in KE plus the change in PE. Okay, so the work not conserved is going to be negative force of friction times the distance over which it travels. To go from B to D, it's going X plus D. It's going this whole distance, right? But the problem is there's no friction while it's going that X, so it's only going to be D, and it's only going to do it once, right? Because it's not coming back. Okay, equals the change in kinetic energy. Well, at B, at D, where it's gone as high as it's going to go, the final kinetic energy is 0. And the initial kinetic energy is at B, where it is also 0. So that's pretty easy. Okay, plus, now we've got some spring energy we have to deal with. So, or I guess we'll start with change in change in gravitational potential energy. So that'll be mg, and now I need the delta y, right? So the delta y it's going to go from here to there. And so this is that angle theta. And that distance is x plus d. So this vertical distance will be x plus d times the sine of theta. X plus d sine of theta. I guess that doesn't need a parentheses, does it? I guess we can just put one there. Okay, and then we've got to deal with the spring. So plus the spring. So at D, its final position has no spring potential energy minus spring potential energy at B. 1/2 kx squared. Okay. All right, so let's do some algebra on this sucker. Okay, this one, the way that I did it here, was way more complicated than the one that I did on the screen, but the problem here is we're solving for D, and D is in 2 terms. So I'm going to have to spread that out. For now, I'm going to leave this as force of friction just because I don't feel like, you know what, I'm not going to do that. Negative mu mg cosine theta times D. Okay, equals mgx sine theta plus mgd sine theta minus 1/2 kx squared. Okay, cool. Let's see here. So I want to get these 2 together. Okay, so I guess I'll bring mgd sine theta over to the left. So I'm going to be left with D out of negative mu mg cosine theta minus mg sine theta equals mgx sine theta minus 1/2 kx squared. Okay, so I hope this algebra is useful for you. I find this to be kind of a waste of time in some ways. This problem was too hard for a test. Of course, that was why I, give you some bonus points for it or whatever. So I'm going to put this on the bottom and I'm going to make everything negative, which means I'm going to switch the signs here, right? So on top, I'm going to have 1/2 kx squared minus mg x sine theta divided by mu mg cosine theta, mu mg cosine theta plus mg sine theta, mg sine theta. Okay, so I don't remember how I did this on the screen, but or on the key, but it was a lot easier than this. Anyway, so here we go. D equals. I'll pause and do all this behind the scenes. Okay, so big nasty equation. D equals a whole bunch of stuff. Okay, so I'm getting D equals 3.6669 meters, which is slightly different than my key. So I'm gonna have to stare at that and see what the error is there, whether or not the error is on the key or if it's on what I just did. And I found it appears the error is on the key. I plugged in a value for the velocity that I have no idea where it came from. Anyway, so I'll post something for errata, but this is correct. All right, so anyway, so now that we know how high, so this distance represents how high this thing will slide up the ramp until it stops, right? So it's going to do that distance up and then that distance back down. Okay, so where are we? We're going to take that distance. I'm going to go way over here. Is this? Oh yeah, it's right here. Wait, is that it? Yeah, this was the whole point of all of it, right? We wanted to solve for this. And ultimately, when we're down here, we want to solve for this right here, VA double prime, okay? So let's try to isolate that now that we know the value for D. Okay, so VA double prime equals, let's see, -2 mu mg cosine theta minus mgx sine theta plus 1/2 kx squared. Okay, so we're going to take all of this. No, sorry, we're going to take this. And so we're going to do m2 over m, 2 over m, and we're going to put a giant square root on it all. So VA double prime equals the square root of -4 on, nope, there's no m left anymore. 4 mu g cosine theta. We're Houston, we have there's a D, right? That D is coming with, right? I was going to say we have a units issue there. Minus 2 gx sine theta plus 1, no, dadgummit. Oh yeah, because we multiply by 2 over m. So this is going to become kx squared on m. Okay, so again, this problem was too hard for a test. Would have been a good in-class learning problem, as long as we didn't get too lost in the weeds like I am doing now with this algebra here. Okay, so again, I'll pause it while I do the algebra. Okay, and I was kind of running out of room, so we're just going to kind of treat this all like this is one giant line. Let's see what happens when we do the calculator here. And I suppose before I, completely plug this in the calculator, we know what answer we want to get, right? So when this thing left the spring, or did it leave the spring? It had a velocity of 7.8 meters per second. By the time it gets back, it's going to be less than 7.8 meters per second, right? Because it's lost energy. So our expectation, depending on how Wagner set how frictional this is, now it's got a coefficient of friction 0.4. So our expectation, I don't know, maybe we're going to lose half of the energy. I don't really know. Okay, but we should be less than 7.8. Okay, that's the only thing that we know for sure. Okay, so let me go ahead and plug in chug. Okay, so I'm getting 3.3223 meters per second. So VA double prime equals 3.3, I guess, meters per second. I can't even see my key. I can't even see what my final answer was there. But you can see that we lost a very significant amount of the energy, right? A very non-zero amount of the energy. Okay, anyway, so that's how you solve it. Obviously, this is too hard for a test, in my opinion, and that was a mistake on my part. So the guys who were taking this test, they got a pretty nice curve, right? I think this one is reasonable but tough. Okay, and everybody should be able to do, well, every honors kid should be able to do this, right? It's tough. It's a hard problem. There's really no way around it. Okay, so that's it. Thank you very much, and I hope this was useful to you. I mean, look at that, scribble. All right, so anyway, hope y'all having a good day. I hope this is helpful. Take it easy.